Okay, this video is for my MAE 3403 computer methods students who are working on final exam doing beam deflection calculations for a particular beam. And so we already talked about, and there's some question about shifting the curves because of constants of integration. We've already talked about starting with our loading curve, which is the left-hand reaction of the beam solved by statics, a right-hand reaction of the beam solved by statics, a distributed load, uniform distributed load all the way across of size W pointing downward, and then a downward point load at a given location. And so we talked about very carefully in class then how to go about and draw and generate a bunch of points on this shear diagram by doing effectively trapezoidal rule integrations to generate the shear diagram. Once we have all of the data points in the shear diagram, we talked about how to use trapezoidal rule integration to generate a moment diagram. Okay, and the moment starts at 0, and if we did the statics right with the left hand and the right hand reactions, that moment diagram will close back to 0 here or very close to it. Once we have our moment diagram done, then what we talked about was integrating the moment diagram in the same way to come up with a slope diagram. This isn't truly the slope, though it's actually the EI, Young's modulus moment of inertia, times the slope. And I'm going to call this EI slope star. We integrate the moment diagram, we generate this graph, and this is roughly what it'll look like. But it turns out that the true EI slope diagram is the integral of the moment plus an unknown constant of integration. That constant is going to shift this slope diagram up and down, because we don't truly have slope at the left-hand end, zero slope at the left-hand end. The 0 point is going to be somewhere in the middle when we shift this thing up and down. So we have an unknown constant of integration from this one that we have to deal with, and it is unknown, and we'll have to find it later. I'm going to pause to answer the. Okay, continuing on after the phone call. Oh, but it appears I moved my screen, so I got to put it back in place. Let me figure out how to do that. That looks close enough, okay? And so what we had was a constant of integration that was unknown when we integrated the moment, and we're going to need to find that constant, and right now there's nothing we can do to find that constant. So what we do is just plow ahead. Let's integrate this incomplete EI slope curve, because it's missing the constant, and we'll get an incomplete EI deflection curve that I'm going to call EI delta star. EI delta, the true slope curve, is this EI delta star, the integral of the slope of the incomplete slope curve, plus the integral of the C1, which would give us a C1x term, and we get a new constant of integration out of this one, which is unknown. But now we know enough about the system to apply boundary conditions and solve for those unknowns, C1s and C2. First boundary condition we're going to apply is that the deflection at the left-hand end needs to be 0. So EI delta of 0 is 0. If that's true, then looking at the EI delta equation, for it to be 0, first of all, at L equals 0, this integral piece is 0. At L equals 0, or at X equals 0 here, this piece is 0 as well. So what that says is C2 has to be 0 as well. If C2 weren't 0, then we'd have some offset deflection here. Therefore, C2 is 0. The other boundary condition is at the right-hand end of the simply supported beam, the deflection there should be 0 as well. So EI delta at L should also be 0. All right, to make that happen, the final EI delta, which should be 0 at X equal L, is the value of our integral EI delta star plus C1 times L plus 0, because that one has already been turned out to be 0. Okay, so this plus C1L equals 0. Okay, that plus C1L equals 0. If that's the case, we can solve for for C1. C1 is equal to the EI delta star at L. That's the number right here. It's my very last EI delta integral number. It's that divided by L with an opposite sign. So C1 is minus EI delta at the very right end. That's EI delta star divided by the length. Once I know the C1, and it's going to be a negative number, I can add that negative number to every value on this curve. It's going to drop the curve down a certain amount. and I'll have some negative slope at the beginning, a positive slope at the end, and a zero slope somewhere in the middle. So that effectively either drops the curve or just shifts the zero line upward. Once I've got that done, I could reintegrate the true EI slope and get the true EI delta, or I could simply recognize the only thing wrong with this curve is it needed a C1x piece added in. So I can take that C1, which is a negative number, and at every x point along my existing data, take the x value, multiply by C1, a negative number, and add it to the current y value. That in effect will shift this curve downward, but it'll have no shift on the left-hand end. And as I move to the right-hand end, it'll have greater and greater shift, so that by the time I get to the right-hand end, it will have shifted this down to 0. And we'll see for this deflection curve a sort of smiley face below the x-axis. So the key thing is this needs to be shifted by C1. C1 is this last number of the integral divided by L. Change the sign. Use C1 to fix this. Reintegrate or patch up by changing each value here by the quantity C1x. That should do it. If you have any questions, send me an email or contact me.